Okay, good morning. Now today we'll see last point of chapter number 3, that is motion or trajectory planning, and we will end syllabus also. After that we'll cover practicals. A motion or trajectory planning. The goal of motion planning of a robot is to generate a function according to which a robot's joints will move. This function generation depends on the robot tasks. For example, to pick up an object from one point to place it in another point, or to weld two metal pieces along a curve. In the former case, initial and final points are assigned, that is point to point motion, whereas in the latter situation, a finite sequence of points needs to be specified, that is continuous path motion. A robot user typically specifies a number of parameters to describe a point-to-point or continuous path task. An algorithm then computes the inputs for the motion controller of the robot. Motion planning, which is also referred in the literature as trajectory planning, can be done either in the joint space, that is in terms of joint positions, velocities and accelerations, or Cartesian space, also called operational space, that is in terms of the end effector positions, orientations and their derivatives. Usually the latter is preferred by an operator since it allows a natural description of the task the robot has to perform. However, the control action on the robot is carried in the joint space. Thus, a suitable inverse kinematics algorithm is to be used to reconstruct the time sequence of joint variables corresponding to the above sequence in the Cartesian space. Motion planning in the Cartesian space naturally allows accounting for the presence of any constraints along the end effector path. These are due to regions of workspace which are forbidden to the robot. For example, due to the presence of obstacles, such constraints are better described in the Cartesian space because their corresponding points in the joint space are difficult to compute. But in the neighborhood of singular configurations, trajectory planning in the Cartesian space is not possible. This is due to the fact that no joint variable can be computed for given end effector variables due to non-existence of the inverse of the associated motion transfer matrix called the Jacobian matrix. In such cases, it is advisable to specify the end effector movement in terms of the joint variables, that is joint space planning. Hence, a time sequence of joint variables has to be generated. For completeness, both types of motion planning are presented in the following sections. Now, first is the joint space planning, whatever it is now specified here. Now, joint space planning. In this section, methods to determine a desired trajectory of joint variables over time are considered. In the joint space scheme, it is assumed that the initial and final joint positions are given or calculated from corresponding initial and final configurations of the end effector or are known from the inverse kinematics solutions for position. Then the basic problem is to solve is how to select a trajectory between a given initial and final joint positions with the time interval allowed to move between them. A simple straightforward approach could be to join the initial and final joint angles denoted with theta naught at time t is equal to t naught or t0 and theta f at time t is equal to tf respectively using a straight line function which can be expressed as theta t is equal to a naught plus a1 t where a naught is equal to theta naught t and a1 is equal to theta tf minus theta t naught divided by tf minus t naught, where theta t is the joint angle at any time t and a1 is the slope of the straight line shown in figure 12.1a, which is constant. This implies that the joint rate or velocity has a constant value of a1 shown in figure 12.1b, whereas the acceleration is 0 as indicated in figure 12.1c. If more than one points have to be connected, a series of such straight lines have to be joined. Therefore, if you will see here a straight line trajectory, here joint angle is there at any time t. This is the joint angle at any time t. The slope of this line is a1. A1 is the slope of the straight line which is constant. This implies that the joint rate or velocity has a constant value a1. Therefore, joint rate or velocity, rate means rate of change of, rate means always remember it is change with respect to time. That is the meaning of the word rate. Therefore, a1 a1 is constant here. If a1 or velocity is constant, therefore acceleration is 0 because differentiation of velocity or constant value. Since velocity is constant, therefore you are knowing differentiation of velocity is acceleration. Therefore differentiation of constant value is always leads to 0. Therefore theta dot constant, therefore theta double dot is 0. Such first order polynomial trajectory is generally not desired due to its discontinuities in joint rates. Note that for a real robotic joint to follow a straight line trajectory of equation 12.1, the actuating motor, say an electric one, will require to achieve almost an instantaneous velocity. This implies that the electric motor must provide an almost infinite acceleration requiring very high current. As a result, the motor may burn, hence such a trajectory should not be used. Now next is cubic polynomials. An alternative choice where both the velocity and acceleration level continuity need to be maintained is to use a third order or cubic polynomial given by theta t is equal to a naught plus a1 t plus a2 t square plus a3 t cube, where the four coefficients a naught, a1, a2 and a3 are calculated from the velocity and acceleration conditions at time t, t naught and tf, that is theta t naught is equal to theta naught, theta tf is equal to theta f and theta dot t naught is equal to theta naught dot and theta dot tf is equal to theta f dot. Equation 12.2b. To calculate the coefficients, first order derivatives of equation 12.2a are obtained as theta dot t is equal to a1 plus 2a2 t plus 3a3 t square. Now, if one substitutes the conditions of equation 12.2b into the velocity expression of equation 12.2c, it yields the following set of linear algebraic equations, that is ax equal to b, equation 12.3a, where the polynomial 4 into 4 matrix A, the four-dimensional unknown vector x containing the polynomial coefficients and the Four-dimensional known vector B of n conditions are defined below. A is nearly equal to 1 0 0 0 1 tf square tf cube 0 1 0 0 0 1 2 tf 3 tf square. X is nearly equal to a naught a1 a2 a3 and b is nearly equal to theta naught theta f theta dot theta naught dot theta f dot. Solution to the set of linear algebraic equations given by equations 12.3 AB can be obtained as x is equal to a inverse into b, which results in the following: a naught is equal to theta naught, a1 is equal to theta naught dot, a2 is equal to 1 upon tf square into bracket 3 into bracket theta f minus theta naught minus into bracket 2 theta naught dot plus theta f dot into tf bracket complete. A3 is equal to A3 is equal to 1 upon 1 minute. A3 is equal to 1 upon tf cube into bracket 2 into bracket theta naught minus theta f plus theta naught dot plus theta f dot bracket complete into tf bracket complete. Therefore, this is the equation 12.3e. Now, next, note that if the relation shown in figure 12.2, that is boundary conditions, now just here, is satisfied by theta naught dot and theta f dot. That is, if theta f minus theta naught is equal to tf divided by 2 into bracket theta naught dot plus theta f dot, equation 12.3f, then a3 is equal to 0 from equation 12.3, which implies that only a second order polynomial is required for theta t. The corresponding coefficient a2 is then given by a2 is equal to 1 upon 2 tf into bracket theta f dot minus theta naught dot, equation 12.3g. Therefore, this is theta naught. This is a differentiation rate of change theta naught dot. Now, this is the value. This is the value of theta f at the time tf. Now, at the time tf divided by 2, this velocity will be maximum. Therefore, theta naught dot. Therefore, this difference between these two lines is theta tf divided by 2 into bracket theta naught plus theta f dot. Now, cubic polynomials with intermediate points. During a robot motion, it is often desired that one or more intermediate points need to be specified. There are also possibilities to specify only velocities or velocities and accelerations both at these intermediate points. If one chooses to use cubic polynomials, there could be n plus 1 segments for n specified intermediate points. It is possible to find the coefficients for each segment as a naught I dot 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 comma a3i for I is equal to 1 to n using the methodology explained in equation 12.3. As seen earlier, only the velocity continuity can be maintained, but not the accelerations. This is illustrated in example 12.1 below. In case only the position of the intermediate points are given and there is no restriction on velocity and acceleration, one can obtain a smooth continuous curve. This is also illustrated in example 12.1. Now we will see this 12.1 example. cubic polynomials with specified intermediate velocities. Assume a robot joint has to move from 0 degree to 90 degree in 5 seconds. The initial and final joint rates are respectively 25 degree per second and minus 25 degree per second. In the intermediate point of 45 degree at time t is equal to 3 seconds. The joint rate is assumed to be minus 8 degree per second. Two cubic trajectories obtained using equation 12.3 are as follows. Theta 1 t is equal to 25 t plus t square minus 13 t cubed divided by 9. And theta 1 t is equal to 4335 divided by 4 minus 860 t plus 919 divided by 4 into t square minus 39 divided by 2 into t cube, equation 12.4b, where first and second time derivatives symbolizing joint velocity and acceleration respectively are given by theta 1 dot t or theta dot 1 t. Theta 1 dot t is equal to 25 t, 25 plus 2 t minus 13 divided by 3 into t square, and theta 1 double dot t is equal to 2 minus 26 divided by 3t. Now theta 2 dot t is equal to minus 860 plus 919 divided by 2t minus 1171 divided by 2 into t square, and theta 2 double dot t is equal to 919 divided by 2 minus 1170. Therefore, this is two cubic polynomials with one intermediate point. See that this is the time and these are the joint trajectory. Trajectory means angles are there. The plots for equations 12.4AD are shown in figure 12.3a. The discontinuities in joint acceleration denoted as acceleration ACN in the figure is clearly visible. Therefore, see here, this is the joint trajectory with respect to time discontinuous acceleration, and this is the joint trajectory with respect to time, figure B, with continuous acceleration. In case one wants to have a continuous acceleration profile, then some existing constraints have to be relaxed. Say the velocity at the intermediate point is not specified. In such a situation, one can put the constraint of continuous velocity and acceleration at the intermediate point. With this, the first two coefficients of the first cubic polynomial joining the initial and the intermediate points can be obtained easily, as a01 is equal to theta 1 of theta 1 0, which is equal to 0, a11 is equal to theta 1 dot of 0 is equal to 25, where the first subscript corresponds to the order of time and the second one corresponds to the first trajectory. The other coefficients are obtained by solving 6 linear algebraic equations obtained from 6 constants, which are the position of the intermediate point expressed using the first and second cubic polynomials, position and velocity of the final point using second polynomial, and the equal velocity and acceleration obtained from two polynomials. If they are expressed in the form of ax equal to b, their elements can be given by a is nearly equal to 390000, 0013927, 001525125, 000011075, 627 0 minus 1 minus 6 minus 27, 1900 minus 1 minus 9. X is nearly equal to a21 a31 a02 a12 a22 a32, and b is nearly equal to minus 10 45 90 minus 25 minus 25 0. Solution of equation 12.5a can be obtained easily using MATLAB, as for the first cubic polynomial a21 is equal to minus 49 divided by 4 and a31 is equal to 107 divided by 36. And for the second polynomial, 1 minute. A naught 2 is equal to 5415 divided by 16. A12 is equal to 5015 divided by minus of 5015 divided by 16. A22 is equal to 1609 divided by 16, and A32 is equal to minus 153 divided by 16. Figure 12.3b shows the continuous acceleration at the intermediate point. In the above example, only one intermediate point was considered. If more intermediate points are considered, the analysis can be similarly extended. On the other hand, if velocity and acceleration are to be satisfied at the intermediate point, the order of the polynomial has to be increased to higher values. Additionally, if the accelerations at the initial and final points are also needed to be specified, then the polynomial order has to be further increased. Now, Quintic polynomial. A typical cubic polynomial plot is shown in figure 12.3. In the third order trajectory, as done in equation 12.2a, one can only specify a total of 4 conditions at the two ends of the trajectory. There is no control on acceleration, hence at the beginning and the end, acceleration values almost instantly increase or decrease. This may cause damage to the motors controlling the robot joints. Hence, one needs to use fifth order or quintic polynomial to satisfy all 6 equations, that is positions, velocity and accelerations at the two ends in order to have a smooth trajectory. A quintic polynomial is defined by theta t is equal to a naught plus a1t plus a2t square plus a3t cube plus a4t raised to 4 plus a5t raised to 5, whose first two time derivatives are theta dot t is equal to a1 plus 2a2t plus 3a3t square plus 4a4t cube plus 5a5t raised to 4. Theta double dot t is equal to 2a2 plus 6a3t plus 12a4t square plus 20a5t cube. The end conditions are taken as theta ti is equal to theta naught, theta tf is equal to theta f, theta dot of ti is equal to theta naught of theta dot naught, theta dot of tf is equal to theta dot f, and theta double dot ti is equal to theta double dot theta naught double dot, and theta double dot tf is equal to theta double dot f. Equation 12.7. Although many smooth functions can satisfy the constraints given by equation 12.7, polynomials of time t are chosen here due to their ease of computation and simplicity of expression. The lowest order that can satisfy all the 6 conditions of equation 12.7 is 5. Substituting the conditions of equation 12.7 into equations 12.6 a to c. 6 equations with unknowns a0 to a5 are obtained as theta 0 is equal to theta 0, theta naught is equal to a0, equation 12.8a. Theta tf is equal to theta f, which is equal to a0 plus a1 tf plus a2 tf square plus a3 tf cube plus a4 tf raised to 4 plus a5 tf raised to 5. Theta dot 0 is equal to a1, theta dot of tf is equal to a1 plus 2a2 tf plus 3a3 tf square plus 4a4 tf cube plus 5a5 tf raised to 4. Theta double dot of 0 is equal to 2a2 theta double dot of tf is equal to 3a2 plus 6a3 tf plus 12a4 tf square plus 20a5 tf cube. Equations 12.8a to f can be put in a more compact matrix vector form as ax is equal to b, where the 6 by 6 matrix A, the 6-dimensional unknown vector x containing the polynomial coefficients, and the known 6-dimensional vector B of end conditions are expressed below. A is nearly equal to 1 0 0 0 0 0 1 TF square TF cube TF raised to 4 TF raised to 5 0 1 0 0 0 0 0 1 2 TF 3 TF square 4 TF cube 5 TF raised to 4 0 0 2 0 0 0 0 0 2 6 TF 12 TF square 20 TF cube. And x is equal to a naught, a1, a2, a3, a4, a5, and b is equal to theta naught, theta f, theta naught dot, theta f dot, theta naught double dot, theta f double dot. Solution to the set of linear algebraic equations, namely equation 12.8g, can be obtained as x is equal to a inverse into b, which yields the unknown coefficients a naught dot 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 af a5 as a naught is equal to theta naught, a1 is equal to theta naught dot, and a2 is equal to 1 by 2 theta naught double dot. Equation 12.9, a3 is equal to 1 upon 2 tf cube into bracket 20 into bracket theta f minus theta naught minus 8 theta f dot minus plus 12 theta naught dot into tf minus into bracket 3 theta naught double dot minus theta f double dot into tf square. A4 is equal to 1 upon 2 tf raised to 4 into bracket 13 to bracket theta naught minus theta f plus 12 theta f dot plus 16 theta naught dot into tf plus 3 theta plus into bracket 3 theta naught double dot minus 2 theta f double dot in bracket complete into tf square, again square bracket complete, and theta a5 is equal to 1 upon 2 tf raised to 5 into bracket 12 into theta f minus theta naught minus 6 into theta f dot plus theta naught dot into tf minus into bracket theta naught double dot minus theta f double dot into tf square. Note that if theta naught dot theta if theta naught double dot and theta f double dot is equal to 0, the relation shown in figure 12.2 is satisfied by theta naught and theta f, theta naught dot and theta f dot. That is, if equation 12.3 f is valid, then a5 is equal to 0 from equation 12.9d. This implies that only a fourth order polynomial is required for theta t. Accordingly, the coefficients a3 and a4 are given by a3 is equal to 1 upon tf square into bracket theta f dot minus theta naught dot, and a4 is equal to minus 1 upon 2 tf cube into bracket theta f dot minus theta naught dot. Using the combinations of fourth order polynomials and straight lines, trajectories for various cases can be determined fairly easily. Therefore, same figure is there, figure 12.2. Note that a quintic polynomial can also be used to plan a motion which passes through 6 specified points. In fact, any unspecified intermediate points require n minus 1 degree polynomials. In this case, however, no control exists over the velocity and acceleration for the quintic polynomial passing through 6 points. The problem can be formulated in the form of Ax is equal to b, where the 6 by 6 matrix A and the 6-dimensional vector B are given by A is nearly equal to 1 0 0 0 0 0 1 t1 square t1 cube t1 raised to 4 t1 raised to 5 1 t2 square t2 cube t2 raised to 4 t2 raised to 5 1 t3 square t3 cube t3 raised to 4 t3 raised to 5 1 t4 square t4 cube t4 raised to 4 t4 raised to 5 1 tf square tf cube tf raised to 4 tf raised to 5, and b is near equal to theta naught theta 1 theta 2 theta 3 theta 4 theta f, where t naught is equal to 0 was assumed. The above formulation is not desired for large size of n as there will be oscillation in the trajectory. In addition, the problem is ill-conditioned and computationally expensive. Now, trajectory with given initial and final points theta naught and theta f. As in figure 12.7, this is the 12.7 again we will say. The trajectory is developed that starts from rest at theta naught, passes through the phases of acceleration, constant velocity and deceleration, and finally comes to a complete stop at theta f. For this purpose, first the value of parameter delta that denotes 1/2 of the acceleration and deceleration period is chosen. Second, the auxiliary points theta 0t and theta f1 are determined using the following procedure. 2 points theta 01 and theta f2 at time t is equal to delta and t is equal to tf minus delta are taken as theta naught 1 is equal to theta 0 and theta f2 is equal to theta f. Next, theta naught 1 and theta f2 are compared by straight line, and theta naught 2 and theta f1 are determined as the points on the straight line at time t is equal to 2 delta and t is equal to tf minus 2 delta. The trajectory segments between theta naught and theta naught 2 and theta f1 and theta f are then determined using fourth order polynomials such that their velocities coincide with the composition of straight lines connecting theta naught, theta 01, theta f2, theta f at boundary points theta 0, theta 01, theta f2 and theta f, and such that their accelerations are 0 at these boundary points. The trajectory segment between theta 02 and theta f1 is specified by the straight line. Thus, the whole trajectory is given by the bold solid line. Therefore, this is trajectory with acceleration, constant velocity and deceleration. See that here acceleration is there. This is the acceleration, this is the constant velocity, and then deceleration is there. Now, example 12.5 trajectory planning for a two-link planar arm. Applying the above method to the two-link planar arm as shown in figure 12.8. See that this is two link, this is the first link, this is the second link. A1 is equal to 1, it is making an angle of 90 degree. A2 is equal to 1, it is making an angle of 45 degree to vertical link, clockwise direction. This is initial position and this is the final position. Now, suppose we choose delta is equal to 0.3 second. Then the first joint angle theta 1 is obtained as follows. First choose theta 01 is equal to 90 degree at time t is equal to t is equal to 0.3 second and theta f2 is equal to 45 degree at time t is equal to 2.7 second. Straight line equation is then obtained as theta 1 is equal to minus 150 t divided by 8 plus 675 divided by 8. Hence theta naught 2 at t 0.6 yes and theta f1 at t 2.4 yes. Yes means seconds. T is equal to 2.4 seconds are found as theta naught 2 is equal to 675 degree divided by 8 and theta f1 is equal to 405 degree divided by 8. Now for the fourth order polynomial between theta naught and theta 02, the coefficients are obtained as a naught is equal to 90 degree, a1 is equal to a2 is equal to 0 degree, a3 is equal to minus 1875 degree, minus 1875 divided by 36 degree, and a4 is equal to 9375 divided by 216 degree. This is the figure, initial position and final position. That is, this link number second is rotated and it will be, this point will be there on x-axis. Therefore, at that time, link 1 will make an angle of 45 degree and this link 2 will make an angle of 90 degree with respect to link 1. Note that theta naught dot, theta naught double dot, and theta f double dot is equal to 0, and theta f minus theta naught d is equal to tf divided by 2 into bracket theta f dot plus theta naught dot. Conditions were used to find the coefficient values for the interval 0 less than t less than equal to 0.5. The joint trajectory is as follows. Theta 1 is equal to 90 minus 1875 divided by 36 into t cube plus 9375 divided by 216 into t raised to 4. For the straight line between theta 02 and theta f1, that is 0.6 less than t less than equal to 2.4, it can be easily obtained as theta 1 is equal to 675 divided by 8 minus 150 divided by 8 into bracket t minus 0.6. Finally, the fourth order polynomial between theta f2 and theta f, that is 1.5 less than t less than equal to 2, can be written as theta 1 t is equal to a naught plus a1 into bracket t minus 2.4 plus a3 into bracket t minus 2.4 bracket cube plus a4 into bracket t minus 2.4 bracket raised to 4, whose coefficients are calculated as a naught is equal to 405 divided by 8 degree, a1 is equal to 1 minus 150 divided by 8 degree, a3 is equal to 625 divided by 12 degree, and a4 is equal to minus 3125 degree divided by 72. Hence, the final trajectory for theta 1 is written as theta 1 of t is equal to 90 minus 1875 divided by 36 t cube plus 9375 divided by 216 t raised to 4, 675 divided by 8 minus 150 divided by 8 into t minus 0.6, 405 divided by 8 minus 150 divided by 8 into t minus 2.4 plus 625 divided by 12 into t minus 2.4 bracket cube minus 3125 divided by 72 into t minus 2.4 bracket raised to 4 for 2.4 less than t less than equal to 3.3. Similarly, the second joint angle theta 2 is obtained as theta 2t is equal to minus 45 minus 625 divided by 12 t cube plus 3125 divided by 72 t raised to 4 for 0 less than equal to t less than equal to 0.6. Theta 2 is equal to minus 405 divided by 8 minus 150 divided by 8 into t minus 0.6, 0.6 less than t less than equal to 2.4, and theta 2 is equal to minus 675 divided by 8 minus 150 divided by 8 plus into bracket t minus 2.4 plus 625 divided by 12 into t minus 2.4 bracket cube minus 3125 divided by 72 into t minus 2.4 bracket raised to 4 or 2.4 less than t less than equal to 3.0. Figures 12.9a to b show the resulting endpoint trajectories for the two joints of the two link arm, whereas figure 12.9c shows the corresponding MATLAB program which generated the plots of figures 12.9ab. For better visualization, figure 12.10 shows the robot analyzes screenshots during the animation of the two link arm. Therefore, this is the joint 1 trajectories and this is the joint 2 trajectory. See that this is the MATLAB program. I will not read this. Now this is the robo analyzer software. During practical, you will understand. We are going to record the practical afterwards. You can see it. How the angles earlier angle was this was 90 degree and this is 45. How slowly that angle changed. These figures indicate that. Now trajectory with given initial, several intermediate and final points. Here a trajectory is obtained that starts from rest at initial position theta naught and passes through intermediate positions theta 1 and theta 2 and stops at the final position theta f. First, the case where the trajectory exactly passes through theta 1 and theta 2 is considered, where the auxiliary points theta 2, theta 1, theta 1, 2, dot, theta f1 are specified as in figure 12.11. The values at points theta naught 1 and theta naught, theta f2 and theta f are same. Moreover, theta naught 2 and theta 1 are on the straight line between theta naught 1 and theta 1. Similarly, points theta 1, 2, dot, theta f1 are determined. One then can obtain the trajectory between theta naught and theta naught 2 and theta 1 theta 1 2 dot theta f1 theta f using fourth order polynomials, and between theta naught 2 theta 1 theta 1 2 theta 2 1 and theta 2 2 theta f1 using straight lines. The final trajectory is shown with bold lines in figure 12.11. In case the trajectory has to pass exactly through theta 1 and theta 2, the number of auxiliary points needs to be increased as illustrated in figure 12.12a. These auxiliary points are determined as follows. Referring to figure 12.12b, theta I2 I is equal to 1 to 2. 1 2 is the midpoint between A, which is nothing but the intersection of the line of, see that this is the figure, trajectory passing near the intermediate points. T is equal to Ti minus delta with straight line between theta I minus 1, that is theta 0 1 when I is equal to 1, and theta I, and B, that is the intersection of the line of T is equal to Ti minus delta with straight line between theta I and theta I plus 1. Theta f2 is equal when I is equal to 1 point, theta I3 similarly obtained. Then segments between theta naught and theta naught 2 theta 1 theta 1 theta 1 theta 1 4 dot theta f1 theta f are obtained using fourth order polynomials, and those between theta naught 2 and theta 1 theta 1 4 theta 1 2 1 and theta 2 4 theta f1 using straight lines as done above. Now we'll see the last point, that is Cartesian space planning. When a trajectory between two configurations of the robot is generated by a joint variable scheme as described in the prescribed section, it is sometimes difficult to predict the motion of the end effector in Cartesian space. There are also cases in which some specific end effector trajectory is required. For example, in arc welding, the electrode should follow a seam precisely. In such other cases, one may wish to generate a trajectory in terms of the position and orientation of the end effector. There are several ways to describe the position and orientation, that is the configuration of the end effector. Since the end effector is a rigid body in the three-dimensional Cartesian space, it has 6 degrees of freedom. 6 variables are required to prescribe the end effector configuration. Once the way is chosen, given path points can be interpolated with a sequence of, say, a quintic, a cubic, or linear polynomials with parabolic blends, as done for the line joint trajectories in the above sections. A trajectory of an end effector obtained this way is very simple and easy to visualize. Alternatively, end effector motions satisfying some geometric features need to be expressed analytically. Therefore, this is the trajectory of a two-link robot arm in a Cartesian space. This is the trajectory for end effector orientation. Earlier it was two-link robot arm, and this is for end effector. See that initial orientation, final orientation. Therefore, this chapter is over and syllabus is over. Now we'll stop here. Thank you very much. Thank you. Thank you. Now you can leave. Thank you very much. 1 minute, I will take your attendance. Please don't leave.